Morning, everyone. I'm just making sure I get everybody in. Um, I see a question up about the homework. Um, I didn't say you have to prove them by induction, but you should be able to prove them by induction. Now, I don't really care about the I to the K one. I'm going to show you a different way to get that one as a bound. um, or an easy way to remember it. But I mean, you should be able to prove the sum of I is n quantity n plus 1 over 2. Um, that's an old, Math 120, I think, question. And the n squared being n plus 1 to n plus 1 upon 6. Um, that one you did in either 120 or 220. So you should be comfortable with using induction because there will be things we'll have to show induction for, to show the correctness of things. There'll be we're going to go over a couple of different proof techniques as we work through these first few weeks of classes. And then after that, we'll be able to draw on the information that we develop when we're analyzing different algorithms. So, it's just developing a way of being comfortable. And pretty much anything that it's written recursively or as a loop, you can prove, iteratively, you can prove with induction. Just, make sure that you have a base case. The stuff I had up, as far as the ones I put in the notes, those I'm not going to grade. At all. I mean, I don't even want to see them. That sounds terrible, but um, I don't mean I don't want to see them, but I'm not going to try to put grades in those because they're ones that you've done. You've seen them. Um, the one that I posted that was from basically from the book. Um, I didn't put the page reference on the book because I wasn't sure if everyone had gotten a book yet. You know what? That's a good time for a poll. Does everyone have, or do you have, I shouldn't say everyone because you don't know what everyone has. Do you have some kind of instance of the textbook at this point? Actually, the book from that you can rent from the company or buy, if you rent or buy the ebook, it does have kind of like the equivalent of what they call participation exercises in the Zai books. They have at each reading, they have some little that's a new feature of the book. Um, since the last time I used it, I didn't use the book last fall. Because I got in I mean last yeah, fall 24, I guess was the last time I taught this. Um, But it looks like most of you have it. It's nice to have some questions that just make sure you understand what's going on so far. You don't really have to do it. So I will post that as I thought I did post it as an assignment. Wait a minute. Where do I have Brightspace open? Easy to look at. Here. Oh, it wanted me to submit. Yeah, I have a book. Okay, there we go. Um, Oh yeah, and I forgot to make it visible. Okay. All right, so there's this thing that I just made visible for you. Obviously the due date has to change. I'll make this due Wednesday morning. This is not gonna, it's not gonna take you long. It's just putting, yeah, you can see it. It's putting these functions in order. So, and the way I suggested doing them is do them in kind of like a big O, or omega type thing, theta type thing. Um, so the smallest ones on the top, bigger ones on the bottom. And if two things have the same order, so say you have n squared and 2n squared or something like that, things that are the same order, put on the same line. And this way you can get an idea of just how things compare to each other, and there's one thing in here. Oh, they took it out. Good. Or I took it out. Probably I took it out. Um, when we're talking about asymptotics, we're assuming they're increasing functions. We don't know too many things that actually the runtime gets smaller when we have more data. Okay, that wouldn't make any sense. So if something is like 1 over n, that's really not falling into an asymptotic type of function at all. So I object. I know some books say that's a constant going to zero. I object to that being called anything. It's not an asymptotic function because it's something that's a decreasing. Huh. And the definitions for asymptotics generally include the words non-decreasing functions. So I mean they can be constants, but they can't be going down to zero. So again, in this one, I'm not asking you on your assignment to necessarily write down your proof or whatever you used to get a value. But just hold on 1 second. I'm sorry, but I see something getting ripped up that looks like it shouldn't be ripped. Okay, so anyway, it is posted. The exercises I gave you, I'm gonna go over. In fact, I'm gonna go over them first. I just have like a little outline for myself what we're gonna do. So I'm gonna go over those things I told you to look at, um, the exercises. I want to get into like a numerical idea of like the difference between n and log n because I don't know that that's really obvious unless, somebody's pointed out to you how vastly different they are. And then, like an analysis, the difference between using a sequential or linear search versus a binary search. And, can we always use one or the other? So, that's basically where I'm going today. And then, we'll see where we are. Everything I'm doing right now is in chapter 1 of the textbook. Um, I will probably maybe over the weekend give you a couple of exercises from there. Um, you should just like look at the exercises, even if I don't assign some of them, because they're some of the things you may see on an interview. I know you don't necessarily believe me on that, but There are a lot of questions from this textbook that show up on interviews. And I know that because students have come back and told me, "Ooh, we did that thing on an interview and we had done it in class." So I knew I got it right. Um, all right. So anyway, the exercises that I gave you to look at over the weekend from class. Um, the first thing was just summations. These you should know. Um, and we're going to do some exercises either today or Wednesday on how these match up to code and why they're important. So, what is the sum of the numbers from 1 to n of the number 1? Everyone should get that one. You can, yeah, n. It's 1 plus 1 plus 1 plus 1 n times n. What's the sum of the numbers from 1 to n of I? So 1 plus 2 plus 3, so on. Right, n times n plus 1 over 2. And again, that's a classic 120, 220 um, question. And as a kid, I don't know if you all saw this, but it's easy to prove as a kid. Well, of course, as a kid, they did 1 to 10 or something. But you can think of it as you have the biggest and the smallest together is n plus 1. The next two, n minus 1 plus 2. Oh, that's n plus 1. And you keep getting these pairings that are all n plus 1. How many pairs are there? N over 2 times n plus 1. So, I mean, that's just a way to just derive the formula. And yes, you can prove it using induction, but that's a simple way to derive it. And an awful lot of these things are easy to just derive. Um, 2 to the I, if you're ever confused, you just, you know, write the numbers down and see the pattern. The sum of I squared from 1 to n. Yeah. N times n plus 1 times 2n plus 1 all over 6. And I just want to point something out to you. Do I need that much detail if I'm looking at algorithms? Or do I just need the big O for that? I really just need big O, right? I mean, this is an actual numerical number. Numerical number, that makes no sense. This is an actual numerical value, but for our purposes in this class, in general, all we want is an order. So the order of this thing, well, the most significant term in the top would be the 2n cubed over 6, which is big O, or actually theta, of n cubed. Oh, and look at this. This is theta of n squared. Hmm. What is the sum of I to the k? All right, now if you know, and I got, there's several articles up, actually, they're posted on LinkedIn about how bad it is how we're letting students down anytime we let them use AI because we are depriving you of thinking things out. And this new, I put Windows 11 on my laptop. I didn't want to. I've been resisting that. Like I said, I resist change anyway, and I didn't particularly like anything I saw in Windows 11. I saw no need to change, but I started getting into all kinds of problems last week with stuff that no longer had updates on it. So I said, all right. It took all weekend. It kept crashing. It finally went through like, I don't know, 8 o'clock last night, which is why I didn't get to even double check on homeworks. I would have seen that I hadn't made it visible otherwise. Um, but I spent quite a bit of time turning off the AI everywhere I could, um, in the settings because I really can't stand that. But the one of the articles I found most interesting is we're not just making it, way too easy to cheat on stuff. Um, I mean, that's part of it, but um, it's making it harder for you guys to even talk, like on an interview, to just spontaneously speak because AI is writing everything for you. You may put down stuff and you communicate mainly. I know my son, he's always complaining. I do tend to text everybody because I'm just too busy to, if I get on the phone, I don't get off. But he's always complaining about my husband wanting phone calls. And he said, nobody does phone calls anymore. He's always complaining that our nieces and nephews don't call. They'll send a text message, or something on social media they blast to the family. Um, but people are losing your generation and the ones behind you, the younger ones particularly, because you at least had some normal time, are losing the whole idea of communicating spontaneously. When you write a text message, you can edit it. When you write an email, you can go back and edit it. But on an interview, you can't go back and edit what you said. You have to be able to answer. And it's just even socially, you have to be able to talk to people. So anyway, avoid it. Don't rely on AI. Okay, I'm going to give you an easy way to remember this. Huh. And it's n to the k plus 1. Yeah, over k plus 1. I don't really care about the over k plus 1 um, because it's a constant. But I'll put it here right now because what does this remind you of? The sum of I to the k is n to the k plus 1 over k plus 1. What does that remind you of? Well, and plus of the junk. Okay, don't forget, there's other stuff going on there. I mean, you see the pattern evolving from the terms that we've got up there. And if we did I cubed, I think the I cubed is actually in the Rosen textbook. I don't know if that's the one you used for 220, but it's in Rosen. Does that look familiar to any of you? Anybody? What's that? Yep. Yeah, in terms of math. See, this is why, people say, why do we need math? You need math not because you're going to do a whole lot of I mean, if you're doing a whole lot of math on an engineering level, you're going to be using software. But you need the thinking. It's the power rule, which makes sense because what was the definition of the antiderivative? What is the definition? How were you taught to evaluate it? And if you take um, Yeah, area under the curve. And then how did they build a formula for that? Ayub, do you remember? They made little rectangles, right? Or little trapezoids and added them all up. This was a limit of a sum. So it makes sense that a summation would become the power rule. Integrals and summations are completely and totally interconnected. The definition of integral is the a summation. So that's why it makes sense. And everybody remembers the power rule. That's one of the things that's easy to remember. What about the sum of 2 to the I? You notice this one, I changed the limits. I made it 0 to n minus 1, only because in most instances in algorithms, you're going to start with a base case of 0 for binary trees and that, where there's one node, the root. So a binary tree, the root is at one level, and the level 0 has one element in it. So usually summations for powers start or go from 0 to n minus 1. Anyone know what that one is? All right, I'm gonna start this off. Okay, if I just look at, well, 1 is 1, right? If I go from 1 to 2, what is that sum? 1 plus 2. You better get this
Three,
right. 3. And if I go to 1 plus 2 plus 4,
7,
1 plus 2 plus 4 plus 8,
15,
1 plus 2 plus 4 plus 8 plus 16.
31, I think.
What is this? What pattern do you see with 3, 7, 15, 31?
2 to the n minus 2, I think. Or minus 1.
Yeah, it's 2 to the n, yeah, minus 1. So the sum up to 2 to the fourth power, 2 to the 0 to 2 to the fourth, is 2 to the fifth minus 1. And if you're ever confused with it, well, when you put in n plus 1, that's you're getting your sum going to n. I put the up to n minus 1. That's all. This will come in very handy. We do a lot of things with binary trees. I mean, in general, again, I'm talking about general stuff. Binary trees are very, very common. So you should be comfortable with the powers of 2. You should, I mean, in general, you should know these summations from calc. Was it 143 or 152 where you do the series? Yeah. It's either 152 or 143, depending on which sequence. You've got the choice of sequences. If you came as a transfer, I think you did 151 and 152. Okay. Um, what about a to the n and n to the a? Is that little o, little omega, or theta? I mean, a to the n, that's exponential, right? That's a constant to a power. So that looks like that's an exponential value. N to the a is a polynomial, n to a constant value. Oops. I wanted to put, I got the wrong color. I didn't want to actually do it this way. Let me rewrite this. Well, no, let me leave it like this. Ah, this is exponential. This I wanted in red. This is polynomial. Exponential is always going to be bigger than a polynomial for a large enough value. So it's little omega. What about a when I use LG, I made a note somewhere. Um, LG is base 2, in case you didn't. I think most people used that notation already, but because again, with computers, we're always using base 2. So, or usually using base 2. It's usually binary. God, I don't know. I'm having trouble with the sizey stuff today. Okay. What is the relationship there? A to the log n and n to the log a. So I have like one or two brave souls, and then the rest of you are just sitting there. Let me give you a hint. Limits would not do any good for this, right? I mean, just looking at limits probably would get you in trouble because by L'Hopital's rule, you don't know how to do the limit of a to the log n. I doubt you do. It's not n minus log n minus 1. Okay, it's not. But how about try taking logarithms? Try taking the log of a to the log n and try taking the log of n to the log a. Well, okay, same growth, but same growth, do we use big O? Theta, exactly. When you do these logs, the left-hand side here is log n times log a. The right-hand side is log a times log n. Hey, they're the same. It's theta. That's going to come in handy. When we do master theorem, that's how we're going to prove it. Now, just as a little point as for big O is what you see the most, even when we write master theorem, we're going to use big O. only because, there's usually a best case of one or something floating around. Um, so in the master theorem statements, we'll say big O. If we have actual numbers without, um, a best case being one, most searches you can say that. But this is something that actually I think is surprising to people because A to the N and N to the A, well, that clearly is the exponential versus a polynomial. But once the logarithms get into the exponent, they become the same. And one more thing, this showing that log of n base b is theta of natural log n. I played that game on Wednesday, right? I did L'Hopital's rule and I used the derivative of natural log instead of the log n base 2. So I was using that fact. And that one is just straight going back to algebra, your logarithm rules. If you look at the log of n base b, that means the power that you would raise b to get n. So if x is the log of n base b, that means b to the x is n. If I take the natural log of both sides, kind of that same trick, I have that x is equal to log of n over natural log of n over natural log of b. But natural log of b is a constant. So the log of n in base b is just a constant times log of n, natural log of n. So all logarithms, and then this is the important part, therefore, all logs are the same order. So, log of, hold on a second. What is that you've got? Ugh. I'm sorry. The dogs are being horrible today. I really apologize. They're just being horrible. I don't know why. I had to throw them out of here before because they were wrestling. And now one of them's eating a sock. And I don't feel like going to the vet to have it pulled out. Okay, so this is important because one of the data structures you may have talked about, maybe not. I know you did binary trees. You may have talked about 2-3 trees. I mean, I didn't get to it over the summer. Um, I think it just in passing. But a 2-3 tree is just you have three children instead of two. Well, actually, you have two children, and then before you start a new row, you put a third child on everybody. And once everyone's got a third child, you swing off a new row. It's just something to make it a little flatter, but does it change the order of the runtime? No, because it's log base 2 or log base 3. They're basically the same. And it's just when you have more children, there's more bookkeeping. So that's why binary tree has virtually no bookkeeping. But you wouldn't want to just have a binary tree for your directories. Your directory searches for an operating system are obviously multiple children. But without that folder system, forget it. Any of you ever try to keep your stuff without folders? It's a disaster. Okay, so that's the exercises I wanted you. I want you to be comfortable with this stuff. So, and that's why that homework is up to do for Wednesday. Just putting the things in order. Prove to yourself that you could do the harder ones, even if it's using the ratio test or something from calculus. If the ratio of something is less than one, it converges. If it's greater than one, it diverges. So, or comparing it to something that you know. If you know that um, n squared is less than 2 to the n, then obviously it's going to be less than n factorial 2. That kind of stuff. So if you have upper bounds and things. Um, because it doesn't do us any good if you can write an algorithm and then use some theorem to come up with a runtime if you don't know which runtime is better. I mean, the ultimate test is always going to be run it, um, which is what your first project will be. It'll be some kind of run something a couple of different ways and look at the clock. Okay. Um, Now, just this is a very short little thing, but I just want to point out if I'm looking at a linear search. Okay, so if I'm looking at a linear search on an array of n elements, what's the worst case of it? So if I'm doing a linear search on 10 elements, it's 10. Oh, 11 if you want to count the fail, whatever. Um, Big deal. What is binary search? Does everyone remember binary search?
Isn't it like when you split it in half and then like deal with the halves and keep on breaking it up until you find what you're looking for?
That's exactly what it is. Binary search is like when you're playing high-low. I'm thinking of a number from 1 to 10. I'm thinking of a number from 1 to 100. If I said I was thinking of a number from 1 to 100, what would be your first guess? Your best first guess?
50?
50. And if I said low, it's lower than that, then you would say
25.
25. And I said it's higher than that. Well, and then you'd cry because you want a calculator, but yeah, no, higher than 25.
Like 32-ish? Like
Well,
33?
37, but you
Oh,
got the right
37.
idea.
I see.
You've got the right idea. So you're going to go about halfway between 25 and 50. And you're going to keep doing that until you get down to one final number. And I mean, assuming you give the truth, um, which is what we call an adversarial argument, what I'm doing right now. An adversarial argument is where you assume you're asking questions like a game and somebody's giving you answers. Now, if any of you ever played a guessing game like this with a little kid, have any of you poll time? Yikes, my mouse. Have any of you ever played a game like that with a little kid, younger brother and sister, or nieces or nephews, or your own child? I'm not talking about, a teenager. I'm talking about like, little kid, 4 or 5. Okay, so those of you who are saying yes, when you play a game like that with the kid, do they lie or do they tell you the truth or do they lie?
They always lie.
They always lie. They want the game to keep going. And at some point I think they don't even pick a number. I think they just say high or low so they don't have to go to bed yet or eat their broccoli or whatever it is they're trying to get out of. Um, but if somebody is telling you the truth to those answers, you're running a logarithmic runtime. Because what is the definition of the logarithm? Well, yeah, oh, it's the power to which a rate. Well, that's bad. It's how many times you can divide by 2. If you write that Euclidean algorithm, it's just divide by 2, divide by 2. And that's how you change something from base 10 to binary, right? You just keep dividing by 2 and keep track of the remainders. So, um, a binary search in the worst case is going to be log n. To get an idea of what that really means, if, make a little table, we'll go to green for that. Okay, so if I'm doing a linear search on 10 elements, what's the worst case runtime?
I'm sorry, can you repeat that question?
If I'm doing a linear search on 10 elements, what would be the worst case number of guesses? Yeah, 10. If I do a binary search on 10 elements,
It would be like 3 or
yeah,
log of n.
log of n, 3 or 4. Figure, so the first guess is 5, and then there's 2 or 3 elements left, and then there's 1 or 2 elements left, and then to 1. So that would be like 3 or 4. I didn't pick a power of 2, so. What if I have 100 elements and
Then it
I'm
would be 100.
searching? Yeah, the linear is going to be 100. What is the binary search going to be on that?
Also 3 or 4? Or like 4 or 5?
Well, what's the log of 100 between? Think of your powers of 2.
10.
10's kind of high. So what are your powers? The finger school of math, right? 2 to the first is 2, 4, 8, 16, 32, 64, 128. Between 6 and 7. The guarantee is 7. What if n is 1,000? Somebody was starting to, when you've given me the log number, you're getting the right idea there. The linear search, 1,000. If I'm not lucky, it's going to be 1,000 steps. But yeah, the log of 1,000 is only 10, right? 2 to the 10th is 1,024. That's a pretty big difference, isn't it? Now instead of guessing 1, 2, 3, 4, I'm guessing 500, 250, 125, and in 10 steps, I've got it. And now the real point of the whole thing. If n is a million, and a million is something we would care about, even 1,000 isn't that big a deal to search. Not with the clock speeds we've got now. But a million. Well, on linear, that's going to be a million steps. Yeah, 20. So I could take a million steps or I could take 20. And big data searches are going to need, it's big data for a reason. And I don't, yeah, I didn't have you guys look up, but does everyone know what your clock rate means? I don't know. It depends on if you've taken 343 yet. Can anyone tell me if I say you've got a clock rate of, say, here, this is going to be a digression. And I know I stopped digressing in another couple of days. We have digressions now because I don't know really what you know. Okay? I some of you have this is one of the last classes you're taking. Some of you took 313 and went right into 323, which is I think a smart move, but some of you may have taken 340 already, or a lot of you took 343, I think, because I know names, which means I had you either in, well, I could have had you in 111 and 211 in the summer, but I more likely had you in 313 or 343. If your computer has a 2 gigahertz clock rate, what does that mean?
How long our CPU takes to process something?
It's actually, that's not a measure of time. Oh, thank you, Keith. It's 2 billion, not instructions, cycles per second. This means that it's got 2 times 10 to the ninth cycles per second. Now, a cycle is one step in the data path. A cycle is basically in most analysis levels, if we ignore the operating system part, it's the length of time it takes to move something from the cache, the level one cache, into the registers. Everyone took 240, right? Did anyone not take 240? Have you taken 240? Only 25 out of 41 people, 28 out of 40. Okay, better. 32 out of 40. Good. My tablet is counting as one person. All right. So, yeah, pretty much everyone has taken that. So, you know that the way we measure things is by the level one cache. Okay, you move something from the level one cache into a register. So that's basically how we count cycles. A statement, like an arithmetic statement in X equals y plus z in high level language, in any high level language. That would translate to load X into a register, load Y. This is, pseudo. I'm sorry, load Y and load Z. Add them, store that somewhere else, another register, and then store that register into the variable Z. This is your standard execution on any kind of von Neumann machine. Okay? So things come out of memory, they go into the registers, then they come out of the registers and go back to the memory. Each one of these statements So that's why I said it's not really instructions, because even a bare basic arithmetic thing is going to be a minimum of 20 cycles to run. And then, if the operating system has to start moving things around, those of you who took 343, you saw that, we tried to pare everything down to the best possible number of cycles, and then if we had to get one piece of information out of the RAM, we blew it up. You went from like 1.1 cycles to 15, because the RAM itself takes like 100 cycles to access. So it throws everything way off if you need to go to the RAM. But you get an idea. If we can do even, 50 million instructions a second, we're doing really good there. But once you're getting into data, you're doing a lot of memory movement. So just to give you an idea, we don't care really that much about these little numbers. But when you get to searching millions of pieces of data and big data, data analytics, AI, I don't know what you know about AI. AI is just probability, right? It's just what's the most probable thing that you want to write, which is why, it's not necessarily right. It's just a good guess, but it's just a guess. And depending on how the algorithms are written or how well they're written, um, it can be not such a great guess. It's very easy to build stuff in on biases and that. But anyway, um, building the data for AI is a lot of searching stuff. A lot of searching data. That's why it uses up so much energy. They're building databases quickly. All right, so that was a digression, but you just need to have some kind of feel of what this has to do with real world stuff. Okay, so let me look at some templates. And again, you may have done stuff like this before. I don't know. People had me for 313. Some of this will look familiar. Okay. Like I said, I recognize names, but the last couple of years I've taught such a variety of courses, I really don't know who I had for what course anymore. Most of you, I just know I recognize your name. And I don't recognize what class it is necessarily. Some of you, yeah. Um, so if I have code, oh no. Why? It hasn't done this in a long time. In fact, I don't remember the last time it did this. It's not reading my pen. All right, the surface is gonna go off for a minute, but I'll keep talking. I want to, I'm going to do some templates with you. Um, so pieces of code and what their runtimes will look like. And that'll motivate us towards, the easy ones are loops. And you'll see some surprising things about loops. Well, not most, a lot of what we'll be writing are loops, but we also write a lot of um, algorithms that start at least recursively. We then turn them into dynamic programming, which dynamic programming builds in recursion and memory. So by storing recursive steps in memory, we can get rid of the obnoxious runtimes for things like Fibonacci. And there are a lot of different um, algorithms that require, I have a feeling this didn't take, recursion for more than, oh, okay, looks like it took. All right, now I just have to authenticate again, I think. I don't know. Yep, I hate this multi-factor thing. I hate that if I don't have my phone right at my side, I can't do anything on my laptop or tablet for school. I mean, I know you're frustrated by the same thing, but it is annoying. Now I have to join again and let myself in again. Okay, letting myself in. I know it is. I'm the one recording it. All right. So hopefully now we're back. Okay. What's the runtime of that loop?
And
Yeah. And what if I have that? You know what? Let me change that a little bit. Let me start with an N here. What would that be? N squared. Good. What if I change that a little bit? Now, how did you get that? Our outer loop is I equals 1 to n of an inner loop, which is j equals 1 to I. Oh, but the sum of j equals 1 to I, that's what? Oh, j equals 1 to I of 1. So the sum of j equals 1 to I of 1 is come on, the sum of 1 if j goes from 1 to I. I. And then the sum of I, as I goes from 1 to n, is yeah, n times n plus 1 over 2, which is n squared. So changing a loop from a 1 to n, 1 to n, and instead just doing a triangular, an upper triangle or lower triangle from linear algebra, so reducing it down, it's not changing the order. It is cutting the time in half, but it's not changing the order. It's still a quadratic order. What if I have this? Let's write the summations. I'm giving you a tool. Don't just try, guessing. I'm giving you a tool that will work. So my outer loop is going from 1 to n squared. My inner loop is going from 1 to I. And I'm summing, again, one statement. Okay, so the sum of j goes from 1 to I of 1 is just I again, right? And the sum of I from 1 to n squared is what? Ayub, how did you get that? How did you get into the fourth? Yep, it's n squared times n squared plus 1. Remember, the sum of I from 1 to n is n times n plus 1. I've got n squared here, so it's n squared times n squared plus 1. Gives me my n to the fourth plus n squared, the whole thing over 2. All I care about is the lead term, which is the n to the fourth. Now, I'm sure some of you at least were thinking n cubed. I want everyone to take a minute, write the summation things. Before I write them. I always hated when somebody gave a question and then immediately wrote the answer, because then once I saw it, of course I knew it. I had no way of telling if I actually would have gotten it by myself. But we're at a point now, this is real upper level stuff. So I think you need to have time to think things out. And work it from the inside out. You should be starting to see things in the chat. Nobody? Nothing coming up in the chat yet? Yep. Okay, so this inner one, the sum of 1 from I to j squared, that's going to be j squared, right? And I'm going to look at that sum from j equals 1 to I. But by our little power rule thing, oh, I'm sorry, I wrote, j squared. The sum of j squared is going to give you, by your power rule, I cubed. And stuff. And then finally, the sum of I cubed from 1 to n is going to give you n to the fourth. So you have to work your way out. Now, one thing I want you to do for an exercise, um,
Professor, I have a question. Why
yeah,
are you working inwards to outwards instead of um
you you
outwards to inwards?
you always work from the. It's always better to work from the inside out. Just like if you're doing distributive property, that's all this really is.
I see.
So and think of the way your loop executes. What loop is going to execute first? The innermost loop.
Right. I see. Thank you.
Okay? Yeah,
Mm-hmm.
it's just, I mean, can you possibly get the right answer the other way? Yeah, but you're more apt to make a mistake.
I
Because
understand.
this is actually the way the stuff is executing inside the code. Now, see, all I'm going to do here is move these squares around. So do this one, and then how many of you think it's going to make a difference which order I do these things? Nineteen out of 39, 22 out of 39 people are off going to the next class already. I'm up to 31 out of 38. Okay, 30, yeah, 31 out of 38. All right, that's pretty good. All right, right, so now what I want you to do is try fooling around with this for Wednesday. Start reading chapter one. Okay, we covered a lot of chapter one today. A lot. Because you know chapter one. I mean, it talks about, searching for the largest number in array, the smallest number in array, both the min and the max at the same time. Then it asks you to be clever about that. Like, could you do a better job than the standard? But you'll recognize a lot of the examples, okay? And then do that homework that I posted. Because among other things, I need something graded also just to verify everyone's around. Okay? I am taking attendance. Zoom, I've been taking attendance on Zoom. Um, but just to verify in case any of you had trouble signing in or something. It's not enough just for me to see you access Brightspace. If I have you on Zoom and the homework is done, then we're safe, we're covered. All right, I will see you on Wednesday. Otherwise, have a good day, guys. And office hours today at 1:30 if you have any problems.
Professor, I have a really quick question.
Sure.
Um, so I understand why it's theta n squared, but so when I was taking 313 with Chin over the summer, we also did the best case scenario and the worst case scenario. Are we
Right.
only doing the worst case scenario
We're
here?
we're basically just doing the worst case.
Oh, okay, okay, now I
Yeah, the
understand.
best case would be one
Yeah.
because yeah, yay, I found it. But best case, I mean, best case is nice to have. I do the same thing in